So I think that everyone is in, so let us start. So this game has been a warm-up, a sort of an introduction of what we are going to talk about. And I'm pretty sure that many of you have played this game before, probably many times. So the purpose of this game is not to win, but actually to put you into the right sort of mood. So what we are going to talk about, the title is Epistemic Foundations of Equilibrium. When I have been preparing for this lecture, I thought that it would probably be a good idea to make sure that I know what epistemic means. So epistemic is theory of knowledge, and the title sounds scary, but in fact, we are not going to, it is going to be a simple story, and the epistemic foundations are really an attempt to model how people think about their opponents. So when you have been playing this game, trying to guess two-thirds of the average of all other people, what you have been doing, you have been thinking, well, what other people are going to write on those papers, how they're going to think about what they're going to write on those papers, and so on. And this is exactly what we are going to talk about today and on Wednesday. So even though my title is Epistemic Foundations of Equilibrium, it is a little bit of cheating, which is appropriate because I have been a mafia yesterday. So I'm not going to try to do very. I'm not trying to build a model or anything like this. This is my opportunity. This is more of my opportunity to talk about what equilibrium, what rationality would imply if we have rational people, what they're going to play, and if they happen not to play equilibrium, then what else do we need to make sure that they are playing in equilibrium? And why I want to teach this, why I decided some years ago that I want to include this topic in my game theory course is because I think that when we try to model something, we are very careful about what assumptions we make while we are modeling. We justify them, we think about them, we talk about them. On the scientific seminar, you probably would spend quite a bit of time discussing the assumptions which you have made while modeling. On the other hand, when we hit the time when we solve the model, we say, well, this is the solution. We find Nash equilibrium, and here it is. So what I want to talk about, why I wanted to talk about this is because I think that it makes sense to keep in mind what assumptions we make when we calculate Nash equilibrium. And I think that ignorance about this issue have led, for example, in the early years of experimental economics to some statements such as that, well, in experimental economics we don't see people play Nash equilibrium, so it means that Nash equilibrium is absolutely useless concept. So we are trying to, we will try to talk about these sort of statements as well. And also it is my opportunity to talk a little bit, to discuss a little bit what we want to do when we model, and it is, and I think that it is actually a great topic for the discussion, and I think that we can, we will talk about this on Wednesday, and I think that it would be a good opportunity for us to discuss what exactly we want to do when we build economic models. So let me just give you a brief outline of what we are going to do. What we are going to do, first we want to say what rational people are, and then we want to derive implication from that notion. We are going to talk about undominated strategies and about correlation between choices. And then we discover that rationality alone doesn't imply Nash equilibrium, and then we want to ask a question, who is going to play pure strategy Nash equilibrium? This question is actually very easy to answer. So we will see a theorem about this, and then we will talk a little bit, so we will go away from epistemic foundations, and we will talk a little bit about motivations for Nash equilibrium, and I hope that I will get that far. And again, that would be, and the motivations for Nash equilibrium would be a great place to finish today's lecture. And on Wednesday, we would talk about mixed strategy Nash equilibrium and the motivation for mixed strategy Nash equilibrium, and then we would see some results about who plays Nash equilibrium or what assumptions we need for mixed strategy Nash equilibrium to be borne out in the real world. And then we will, I will introduce another concept, which is correlated equilibrium. And we know that we use Nash equilibrium. We know that we don't use correlated equilibrium. And I would try to say that it is an appealing concept, and it would be interesting to think about why we want to use Nash equilibrium as opposed to say correlated equilibrium. So correlated equilibrium is not something which this is a concept which I want to talk about, not particularly because it is so cool, but to just make a distinction between Nash equilibrium and something else. So, and if we have time, I don't think that we are going to have time, we might see a little bit of formalism in the epistemic foundations, which is in interactive belief system. I would ask you to ask questions as I go along, and so your goal is to make sure that I wouldn't hit the last bullet point. So let us begin by thinking what we would call rational strategy. If we look at this matrix, I'm sure that everyone knows how to read this matrix. It is two players, player one who is choosing rows, player two who is choosing columns. And we are thinking about player one, and we are thinking what strategy of player one is rational. So if you look at this matrix, you would say that, well, obviously strategy U is rational. If player two plays left, then of course you want to play up and obtain the highest possible payoff. The question is, what about strategy M? Is strategy M rational? So when we think about rationality, we think we allow the rational player to have any belief. Why we allow a rational player to have any belief? Because a rational player might think that other player is not rational, that other player actually choose right all the time, no matter what. So we don't make we don't make any assumptions about rationality of the other player. The player whom we are thinking about just forms some sort of belief about the other player, and then if this player is rational, that player should behave according to this belief and maximize his payoff or her payoff given this belief. So when we talk about rationality, we say that we don't impose any restrictions on the beliefs of the player. We impose restrictions on how player should behave given the belief. So in this particular matrix, if player one thinks that right is the strategy which the opponent is going to play, then that player would choose M, and it would be a rational thing to do. And in fact, if player 1 thinks that it is either left or right with equal probabilities, then he would choose D, and it would be a rational thing to do for him in this case. So this was an introduction to my first definition. So, and the first definition says exactly what I have said in words just a second ago. It says that you form a belief, and then you choose a strategy which maximizes your payoff according to this belief. So this looks somewhat similar to the definitions of undominated strategies and things like this. So I want to stress a few differences. First of all, sigma j is the belief, it is not the strategy of the opponent. So we don't talk about strategies of the opponent at this particular second. We only talk about that particular player and what he believes in. And another thing is that it is in fact immaterial for the rationality what player J is going to play in reality. So what we want to do next is we gave this definition of what rational player is going to do, and we want to map this into some language which we have seen before, which we have talked about. And to do this, let me give you the definition which you surely all know. So what I want to give a definition of dominated strategy and undominated strategy. So the dominated strategy is the strategy which, so it is, yeah, so the strategy is dominated if you can find another strategy such that it will work better than the given strategy for each possible belief, for each possible strategy of the opponent. And if strategy is not strictly dominated, then it is undominated. So what we want to, as I said, what we want to do, we want to map the rational behavior into undominated strategies, and we will see that those two things are, for now, they are equivalent. And I have forgotten to mention what is written on the top of the slide. Now I switch to talking about two-person games, and we will get back to three people games later in the talk. So this is my first proposition, that if player is rational, the only thing which we can get out of rationality is that he plays undominated strategy. So it means that if player is rational, we cannot get anything. Not only we get this, but also we cannot get anything more than that. So why it eventually would be interesting is because when we talk about Nash equilibrium, then we know that, from that sort of propositions, we would know that we cannot get to Nash equilibrium from simple rationality. So let me So let me just sketch a proof of this proposition. It looks almost obvious, but it is actually, it does require a little bit of work to show that that rational strategies, that undominated strategies, that it is no undominated strategy which is, this is no undominated strategies, strategy which is rational. So let me check whether it goes this way or the other way. So if we have a rational strategy, then we know for sure that it is undominated strategy. But if we pick undominated strategy, then it would be that this strategy is not rational. So maybe we can get something more from undominated strategies. So again, the one direction from rationality to undomination is obvious, because if you just look at the definition, if strategy is rational, then it means that it is a certain belief. Now we would say that this certain belief is actual strategy which the opponent plays, and it means that this inequality doesn't hold for at least one strategy. It means that this strategy is undominated. Now imagine that the strategy is undominated, and then I want to show you that rational player may play this strategy. What it means that rational player may play this strategy, it means that I can find a belief such that the rational player is going to play this strategy. Remember the definition of rationality. The definition of rationality is that it is a strategy, that it is a belief such that it makes the strategy worthwhile. To show you this, let me restrict my attention not only to two players, but also to just two strategies of the opponent. So imagine that opponent has two strategies, and I'm going to map map utilities on this graph from playing a particular strategy against one strategy of the opponent and another strategy of the opponent. It is what? Uh-huh. Yes. I want to show you the proof, but I don't want you to understand the proof. So let me try the black marker and let me try to make it bigger. So this axis is going to be the utility of player 1 from playing a particular strategy, which is a dot, against the strategy S1 of the opponent. This axis is going to be the utility of player 1 from playing this strategy dot against the strategy 2 of the opponent. So I'm going to pick a strategy like this one. And this particular strategy would give me, say, 4 if it is played against this strategy, and say 2 if it is played against the other strategy. So I'm going to go over all my strategies, all the strategies of player 1, and I'm going to map them something like this. So let me check whether it is what I want, not exactly. On this graph, I can see which strategies are dominated and which strategies are undominated. For example, if I look at this strategy gives me higher payoff if I use it against strategy 1, and this strategy gives me the higher payoff if I use it against strategy 2. So it means that if I compare this strategy and this strategy is better. So what strategies which are better than this strategy? It is everything inside this hull of this strategy. If I look at this strategy, then I can see that this strategy doesn't dominate this strategy, and this strategy doesn't dominate this strategy, and obviously those don't. But remember in my definition, I haven't stressed it, and I actually have, yeah, I haven't stressed this, that the belief is some mixture. I have referred to it when I have been showing you the picture, but remember that we are talking about the mixtures on belief. You can believe that opponent is playing half left, half right, which means that even though this strategy is not dominated by any pure strategy, I can construct a mixed strategy which will dominate that strategy. So why do we need this picture? This picture shows us all our undominated strategies. We just draw a hole for each strategy, and then we have a curve of what we can have as undominated strategy. Now, for each of that undominated strategy, I should write down a belief which would rationalize playing this strategy, which is to say that it maximizes your utility given your belief. So I have to show you this belief. And for example, when we looked at this strategy and compared to, when we looked at this strategy and compared to this strategy, then the belief which rationalize playing this strategy against this strategy is actually very simple. Let me draw it like this. So it is the belief that the opponent plays strategy 1 with probability 1 and strategy 0 with probability 0. If I look at this strategy, then what the mixture has been, we can say that it is half-half, and again I will draw an arrow to indicate that it is the belief half-half. So how can I persuade you that for any strategy which is on the outer in the outer region, I can find a right belief? So what it means that I play a particular strategy. What it means that this strategy is the best response. I can draw a line like this, and what pays me more would be on the right-hand side of that line. What pays me less would be on the left-hand side of the line. If you just write the equation for this strategy, you would see that the equation for this strategy would give you exactly the payoff from playing this strategy. So I draw a plane like this. I write the equation for this plane, and the equation for this plane give me exactly the payoff at this point. So everything which is to the right of the plane gives me higher payoff. Everything which is to the left of the plane gives me a lower payoff. So now I have reduced my goal in finding the right belief in just drawing a plane which separate the payoffs which I can obtain from playing strategies from the payoff which I cannot obtain. So I want to draw a plane such that everything which is above the plane give me higher payoff, everything which is below the plane give me lower payoff. You see that for this strategy, I couldn't possibly draw such a plane because however I draw it, some of the payoffs are going to be above the plane, some of the payoffs are going to be below the plane. On the other hand, if we look at the strategies in the outer line, you would see that I can easily draw a plane such that all possible payoffs from the game are below the plane, which means that this playing this particular strategy give me the highest payoff against this belief described by this plane, than any other strategy could give me. So I realized that writing an equation for the plane probably have been a good thing to do. So let me just stop for a second here and ask you for questions, or just give you a little bit of time to look at the picture. Yeah.
Was there a dot further to the right, or is that imaginary?
This one? Yes. It was a dot. I have forgotten about it. Sorry.
That changes everything.
Sorry. Yeah, I thought that it is just a dot. Yeah. No, yeah, sorry about this. Right, so again, the goal has been to find the belief which rationalize my choice, and to do so, I have drawn all the undominated strategies, and I have drawn a plane which separates strategies which can be played and strategies which payoffs which you can get from playing strategies and payoffs which you cannot get from playing strategies, those and those. And then if I just write the equation for this lane, it would give you the right belief. So what is an intermediate takeout from this is that now we sort of believe that this proposition is true. Now we believe that the only thing which we can get out of rationality is that people play undominated strategies. Let us now move on, and let us now look at this game which I showed you in the beginning, and think what else we can say about this game. So I think that the reason why I thought that you would think that the only rational strategy here is U is that you would be implicitly assuming that not only I am rational, but also the opponent is rational. So if you do this logic, if you say that, well, I know that I'm rational and I know that my opponent is rational, so if I know that my opponent is rational, then I know that he is going to play L and not R, because L always gives him higher payoff than R. And in this case, you would play U and not M and not D. But I want to draw your attention that to get to this point, we cannot just say that player is rational. We have to say that player is rational and he knows that the other player is rational. So for two-player games, we can state the following theorem. I'm not going to talk about this theorem in as many details as I have talked about the proposition, which says that if we think about player being rational, knowing that player is rational, knowing that player is rational, and so on and so forth, if we have a common knowledge of rationality, then we know that the only thing which we can say players play is iteratively undominated strategies. Yep. Common knowledge necessary in this game? In this game, we only need 2 levels. But to make a general statement, about when iteratively undominated strategies are going to be played, we need full common knowledge of rationality. And in particular, in the game which we have played in the beginning, the iteratively undominated strategy is 0, and you can easily see this by by just thinking about your opponent in this iterative way, we don't need to think about equilibrium or anything. We can just think, well, if people all write 100, then you would be best to write 2/3 of 166. If you realize that people realize this, so it lists this. If you realize that people understand this, then you would continue, so on and so forth, all the way until you hit 0. So this is, I think that I have it on my slide. No, I don't. So this is so the interesting question is how strong the common knowledge of rationality, and we would see on Wednesday how many zeros we have had in the game we have played. So whether we have believed that people are rational and know that everyone is rational and so on and so forth. No. So this is exactly the message which I want to get across, that if we assume that it is a common knowledge of rationality, yeah, so let me repeat the question. The question has been whether common knowledge is necessary and sufficient for Nash equilibrium. So my answer is that this proposition exactly says that it is that if we have common knowledge of rationality, the only thing we can get out of this is iterative elimination of dominated strategies. We don't get Nash equilibrium. And it will be actually interesting to see what exactly we need for Nash equilibrium. So remember my caveat on the previous slides that we have restricted attention to two-player games. And I think that in what I have said so far, it was absolutely no surprises. It was all very reasonable. We take rationality and we arrive at undominated strategies. It's something which we would have expected to begin with. The unexpected part comes from this caveat that we are talking about two-player games, and when we hit three-player games, then the story is actually a little bit more subtle. So let us think about this three-person game. So in this game, in this game, the player 1 chooses up and down, player 2 chooses left and right, and player 3 chooses matrix A, B, and C. I don't care about how player 1 and I don't care what payoffs of player 1 and player 2 are, because again, we are going to talk about rationality. We are not talking about rationality of player 3. We are not going to talk about rationality of player 1 and 2, so it doesn't really matter what payoffs they have. So the question which I want to ask is whether playing strategy B is a rational thing to do. If you look at the payoffs, you see that if UL is played, then strategy A gives higher payoff. If DR is played, then strategy C gives higher payoff. Yes, right. And it is actually some extra payoff from UR and DL. If UR and DL are played, you have extra payoff from playing A and C. So let us check whether it seemed to be rational to play B or seemed to be irrational to play B. And to do so, let us assume that player 1 plays a strategy up with probability alpha and strategy down with probability beta. Alpha and alpha plus beta is obviously 1. And let us assume that player 2 plays strategy L with probability P and strategy R with probability Q. So the joint probability of each cell is just this. I just multiplied the probabilities. And if we now write the payoff for from playing strategy A, strategy B, and strategy C, we would see that if you play strategy A, then what you get is alpha P plus alpha Q, which is alpha. If you play strategy C, then what you get is beta by the same calculation. And if you play strategy D, then B, then what you get is you get alpha P times 07 plus B Q times 07. And imagine that alpha is bigger than beta, then the maximum you can get is by taking P equal to 1. So it means that the maximum you can get is alpha times 0.7. So if alpha is greater than beta, then and P, then the whole expression is maximized when P is equal to 1, and it means that the maximum you can get is alpha times 0.7. Yeah, this is right. Right? So it sounds like playing strategy B is irrational thing to do. Because if you play A or C, you get higher payoff than you could possibly get from playing B. Let us now check whether strategy B is undominated strategy or it is not, and let us check whether A dominates B. We look at DR entry. So imagine that the opponents play D and R, and we see that strategy A gives you 0 and strategy B gives you 0.7. So strategy B actually performed better than A. So maybe strategy C dominates B, but we can do the same. We look at UL. UL gives you 0 if you play C, and UL gives you 0.7 if you play B. You can convince yourself that even if I mix those strategies, then I would get, I would always be able to find the entry either UL or, either DL or UL such that the strategy B is undominated. At most, I would get 0.5, and that strategy gives you 0.7. So you see that now something which we have thought is completely obvious, that rational strategy, common knowledge of rationality imply playing iteratively undominated strategies breaks down, which is, I think, a little bit surprising. And now we are going to think about the reasons why this could happen. So what are we missing from our picture from when we talk about rationality of the players? when we have this sort of breakdown in the relationship which we have thought is completely obvious. Yep.
Is that are you talking about necessity or sufficiency right now?
Necessity of what and sufficiency of what? I'm talking about. Oh, I see. So you mean
which direction of the argument? Which?
I'm talking about strategy B being
rational does not need to.
So it looks like it is not rational from this argument, but it is undominated.
Right. So the only if basically in the statement before.
Yeah. So if it is undominated, then it is rational. No. So, sorry, as you said, it is always very confusing to think if or only if and exactly where the argument goes. So let me just state it again that we have observed that this strategy looks not rational and but undominated. So I want to convince you that there is a way of thinking about that the way I have described rationality in this particular case is actually a restrictive way of describing strategies of the opponents. And if we assume something which is going to be correlation, then we would get this connection back. So what do I mean that we assume correlation? Let us assume that player 1 and player 2 don't do independent randomizations, but do dependent randomization. Let us assume that they never play UR or DL. If one plays D, then the other one plays R, and if, sorry, is it what I want? Yeah, right. So if one plays U, then the other one plays L, and if one plays D, then the other one plays R. So we can now calculate the payoffs from playing strategy A, strategy C, and strategy B from this, and we would see that it is 1 times 0.5 plus 0, or 0 plus 1.5. Against that correlated strategy, the strategy B gives you higher payoff than playing strategy A or strategy C. So if we do allow for correlation between other people's choices, then we again arrive at this theorem which I have shown you. So we can ask a question whether we want to think about correlated strategies or whether we don't want to think about the correlated strategy. And Bob Aumann provides a very nice reason why we should think about correlated strategies. And the reason is the following, that if you know that two people whom you are playing against, player 1 and player 2, have had some common experience, like a business school, then you can say that, well, I don't know what they're going to play. They might be playing up or down or left or right, but I know that they have been taught to make a choice, and their choice is going to be correlated. So this is on one hand, it gives us the connection which we have seen for two-player games back. On the other hand, it shows you that there are some subtle things which we should be aware of when we talk about those issues, but also this actually gives us a good introduction of what I'm going to talk about tomorrow about correlated equilibrium and what is the good solution concept. So let me now finish with pure notion of rationality. Again, now we know that what rationality gives us. We know that it only gives us iteratively undominated strategies. It doesn't give us Nash equilibrium. And let me move to the next question, which is, so if rationality doesn't give us Nash equilibrium, what exactly do we need for Nash equilibrium to be played? And pure strategy Nash equilibrium is quite an easy story. So let me just talk about this. And then we will move to mixed strategy Nash equilibrium, which would have plenty of complications, like that one. And we are going to talk about this tomorrow. So just a short reminder, pure strategy Nash equilibrium is something which maximizes your utility given the choice of the opponents. So if we look at this definition, we notice we can sort of immediately see what we need for Nash equilibrium to be borne out in the real world. So what we have said in this definition, we have said that I know what my opponents play, and given what my opponents play, I play my strategy, which is exactly what this theorem says, that for Nash equilibrium to be played, it is necessary that you would know the strategy which opponents play. So you see that in this theorem, it is nothing which says anything about rationality except for one level of rationality. So people often talk about Nash equilibrium by saying that, well, for Nash equilibrium, we need common knowledge of rationality and things like this. You see that this theorem would tell us, and we can convince ourselves that this theorem is right from the definition, it is no need to have any common knowledge of rationality for equilibrium. The only thing which you need to know about your opponent is that he plays this particular strategy. You don't really need to know that he is rational. You only need to know that it is this strategy which is being played. So this is one point. Another point is that, but what you do need to know is what is being played. So let me trace those two observations back to what I mentioned about experimental literature, which have been saying that in the beginning of when it started, they ran experiments, and they have been saying that, well, we run an experiment, and we know what Nash equilibrium is, and people don't play Nash equilibrium. So this means that Nash equilibrium is just not the right solution concept, and this is right. So for that game which they proposed, it is not the right solution concept because the assumption behind Nash equilibrium is that somehow, it is not clear how, but somehow people know what other people are going to play. In the experiment, it is necessary that in the experimental design, the designers don't tell people what they are supposed to play, naturally, but then it means that the basic assumption for Nash equilibrium is not satisfied. People don't know what other people's play. So I want to keep in mind this theorem, and now I want to go and talk a little bit about motivations for Nash equilibrium. And I think that, so some of them are, on one hand, it is clear what people want to say when they say this, but on the other hand, I would argue that it is a little bit misleading when they say this. And let me start with citations from Krebs and from Gibbons. So, and they are all about multiple Nash equilibria. What they say is that, well, when we have a single Nash equilibrium, then it is all good, and then the solution concept of Nash equilibrium makes sense. On the other hand, when we have multiple Nash equilibria, then the concept of Nash equilibrium becomes more problematic. So on one hand, we sort of feel that this is probably right. We sort of know that it is one equilibrium. We know what people are going to play. And if it is multiple equilibria, then you are unsure about what kind of strategy the player would adopt. But on the other hand, it's all, for this logic to be true, it is necessary to think, to assume that players are actually playing some equilibrium, and then multiple equilibria is a problem. On the other hand, you don't necessarily know what players are going to play, and in this case, even if it is a single Nash equilibrium, it is a problem. So let me just argue that multiple Nash equilibria is not necessarily a problem at all if you know what strategy is going to be played. And this is a very personal experience. So as you know, in Australia, the driving happened on the different side of the road. So it is, here it is. Different side of the road. Sure. So here it happens on right, and in Australia it happens on left, right? Yes. So this is the game which we are going to, which we play all the time, the upper one. So if you are in Australia, then you play left, and other player play left, and we get a certain payoff. If you are in Russia, then you play right, other player plays right, and we get certain other payoff. So it is two Nash equilibria, but we don't have any problems of people driving on the left side of the road in Russia. Well, maybe we do, but in Australia, we don't have a problem of people driving on the right side of the road. Moreover, imagine the situation when I came from Australia and I'm in an empty road, and it happened that it is some other Australian which is also driving on this side of the road. We actually would be very happy to play left-left equilibrium, right? Because this is what we used to do. But we know that everyone is playing right equilibrium. So even though it gives us the right lower payoff, then we would still stick to the equilibrium RR, because we know what the opponent is playing. And just to continue with this sort of criticism of this line of reasoning about multiple Nash equilibria, I just want to point out that it is actually plenty of countries which drive on the right side of the road. It is quite a few which drive on the left side of the road. They are, so the right-sided countries are red, the left-sided countries are blue, and the mixed color countries are the ones which switched between left and right at some point of their history. And this is the sign which unfortunately you cannot see, which is very exciting. It is on the border between two countries. One country drives on the left and the other country drives on the right. So the top sign says that now you have to switch to the other side of the road. So, I mean, in principle, it is no problem with playing in equilibrium when it is multiple equilibria, if you know what opponents play. And as we know from the experiment, single equilibrium doesn't necessarily help. It is also another line of reasoning behind Nash equilibrium, and this line of reasoning says that, well, imagine that we talked before we played a game, and we have agreed to play some other strategy, and then we go to the separate rooms. Remember, we take our decision independently, and if we have agreed on Nash equilibrium, then neither of us has incentives to change their strategy. So that sounds like a reasonable motivation for Nash equilibrium, and it often is, but on the other hand, let me show you this game, which is due by Aumann, in which he tries to argue that this logic might be flawed, might be not right. So what happened in this game? In this game, we have two equilibria. First of all, the story behind the game. We have a nuclear shield, and we can, so it is United States and Russia in all times. We can upgrade our shield and build a new one, which would be very powerful, but it costs money. So if we play the new strategy, then we move to the equilibrium 7-7. If we stay with the current one, then we don't spend those money, we are well protected, and we have 9-9. On the other hand, if someone moves to the new one and someone stays with the current one, then the one who stays with the current one is actually in trouble, because it doesn't have a technology, so the payoffs are 0 and 8. So it seems to be very clear. It is two Nash equilibria. We can play one, we can play another one, and imagine that players came into the room and said that let us stick to the current one because it is a better equilibrium. So I talked to that person who was trying to convince me that we should stick with the current one, and I go into my room and think, well, imagine that that person whom I just talked to, he intended to play strategy new, right? What this player is going to tell me? This player is actually very interested in me playing the strategy current. So he would try to tell me, let's play current, even though he is going to play new. So then the question is, what we could get out of this communication? And we can get nothing, because we know that if he decided to play new, then he would say exactly the same thing as if he decided to play current. So again, he has the incentives to do so. That's right. So in this particular game, he has incentives to tell you that he wants to play current. But the motivation for Nash equilibrium, remember that it was that if we have talked to each other and we have said that we are going to play new, then we have no incentives to deviate. So it is true that in this particular game, if I know that you are going to play new, then so if I know that you're going to play new, then I would get 7 from playing new and 0 from playing current. But the question is what I can get out of the communication with you when you tell that you are going to play current. Would you believe me that I'm going to play current? Not necessarily, because even if I'm going to play new, then I would try to convince you that you should play current. So it is not a good strategy for you to switch from new to current or from current to new, but it is good strategy for you to try to convince the other player to switch.
Yeah, but my problem is that.
I think that you have to switch
Yeah,
it.
but I don't think any player has an incentive to. Sorry, to transmit that information. I mean, to convince. If I would like to stick to new, I would like you to choose the current. But I don't think he has an incentive to transmit such information.
So imagine that I decided to play new,
Yeah.
and
But,
my
but
payoff.
why do you decide to play new?
Imagine that. So I'm thinking about the other player.
Yeah.
I don't know why he might decide to play new.
Yeah.
I'm just trying to think about the communication which has happened in the room.
Yeah.
And the communication would be the same whether he decided to play. So imagine that he come to the room thinking about a particular strategy which he's going to play.
Yeah.
The question is, would he ever tell you that he's going to play new? The answer is not. He would never tell you that he's going to play new.
Yeah.
He would always tell you that he's going to play current.
I get your point is that, and this information is meaningless, right?
This communication is meaningless.
Yeah.
That's right. This communication is meaningless, and again, why I am bringing this particular game in is because it is important. It is not enough to just talk about a strategy. You have to really know, as the theorem says, that you have to know what other players are going to play. So if it is one shot, you just look at the game. Even if you talked, then it would not necessarily help you in arriving to Nash equilibrium. It is knowledge which is needed to arrive to Nash equilibrium. Let me finish with a couple of quotes. The first one is actually very hard hitting at Nash equilibrium, and it is from Osborne and Rubinstein. And they say that the typical interpretation of the game is that people look at the game, people are rational, people don't know anything about the game except the payoffs, and probably that they are rational. They might know that the other people are rational. So each player is unaware when choosing his action of the choices being made by the other players. So this is a typical assumption. But in this case, as we have seen from the previous theorem, Nash equilibrium assumptions for Nash equilibrium are not satisfied. And let me switch to another one, which sort of concludes what I wanted to talk about today, from Adam Brandenburger, who says that, when we think about whether Nash equilibrium is going to be a good prediction for a particular game or whether it is not going to be a good prediction for a particular game, we have to think whether the assumptions behind Nash equilibrium are satisfied, and this assumption, which I have been talking about in length in the last 10 minutes, is whether players will predict correctly other players' choices. If they would, then it is a good solution concept. If they wouldn't, then it is quite possible. Then we shouldn't expect that the play of the game will result in Nash equilibrium being played. So the message from what we have seen today is proceed with caution when you use Nash equilibrium. Just a word of, given that Andrei is going to teach conflict theory in just an hour, so I don't want to stop at this very negative note toward Nash equilibrium, because I imagine that he is going to find plenty. And my message for the next time is going to be much more positive. So it is still proceed with caution. Remember what assumptions for Nash equilibrium are, but there are good reasons why we do stick to Nash equilibrium as opposed to some solution concepts which might look to be more appealing, like correlated equilibrium, probably, or something else. So there are good reasons why we want to why we still want to stick to Nash equilibrium and not use something else. And this is what we're going to talk about next time. That's all. I think that I'm a little bit over time. And by the way, when I'm talking about motivations, I certainly express my own opinions rather than trying to share scientific knowledge. So obviously, people could have different opinions about motivation, and it would be great if they express it them.
One small question. What will happen if we, to the concept of a rational strategy, if we add some kind attitude to risk? For example, in your example, yes? Can you show us the first one?
The very, very first one?
Yes, the very, very first. No. Yes, the matrix, yeah. You said before that the strategy D can be rational if we assume that player 1 believes that player 2 choose the strategy L and the strategy R with equal probability, yes? But if we assume, for example, that the player 1 is risk lower, in this case, the strategy D will not be rational, if I understand this point correctly. And can be, I want to say that it can be not rational in this case. Am I right? Yes. And
I imagine that if you so again, we look at the individual which we look at this individual and we are trying to think whether after observing this particular choice, this individual look to be rational or not. So if you ask whether you can imagine some situation when this choice is not rational, you can. And you don't need to be, you don't need to think about risk loving. You can just say, if he knows that the other player is playing left, then this choice is not rational. So I think that you are switching the goal. You're switching the goal around. So my goal has been to figure out whether it is possible that this player is rational, and you are sort of asking whether this player is always rational. I mean, whether for anything which could happen, this player is rational. So obviously, it is not that for anything which can happen, this player is rational.
Well, sociologists and anthropologists would say that there is no common knowledge among all people. And does it mean that this theory works only for Western countries? Because when you say about utilities, people from different countries can put their own meaning on their wage, on their numbers. And if we speak even about money, people from different countries, and moreover, people who get money from different resources, they would calculate the same amount of money in different ways. That means that it's very problematic to use this theorem for, I don't know, for interaction. People who are going to do business from and China and Russia maybe. What do you comment on?
So first of all, in this matrix, we are ignorant about how those numbers came from. So it could be that I think that you are thinking about those numbers as sort of money being paid. I'm thinking about those numbers as being just utilities, and how those utilities came about, I don't know. So maybe it is that people don't like money and they get the utility of 3 from being poor and the utility of 1 from being rich. So it is on one hand. On the other hand, you mentioned that theorem is being applicable or not applicable in Western or non-Western societies. So I think that, first of all, theorem is theorem, so it is applicable everywhere. The assumptions might be wrong or right in one society or another society. I can assure you that the winning number in the game which you have played in the beginning hasn't been 0. And it is never 0 in Russia, it is never 0 in Australia, it is never 0 in US, which just means that we are not commonly, we don't commonly know that that everyone in the room is going to behave rationally. So again, it is not that we don't, it is not enough to say that I don't think that that guy is rational. It is enough to just have breakdown in rationality in a much higher level. So I think that he is rational, and I think that he thinks that I'm rational, but I think that he thinks that I'm thinking about him as not being rational, and this is enough.
Just to put some words into your mouth, I would read this as kind of saying we need to design and think about games with dominant strategies, because then we are kind of safe.
I agree. So I think that you are thinking about you are thinking about mechanism design perspective, and it is true that mechanism design. So the situations when we can design a game which is going to be played is moving more and more toward trying to use dominant strategies as opposed to Nash equilibrium. On the other hand, quite often we are not in the mechanism design situation where we don't design a game, we just try to analyze how this particular game is going to be played. And in this case, we cannot just say that, we can make a prediction that we can only eliminate undominated strategies and then be left with a huge number of strategies and say that this is our prediction. So this is one way, and this is actually what we are going to talk about next time. Or we can try to refine our prediction, and then we have to rely on something. So I think that in mechanism design, it is absolutely right. I think that it is much more questionable when we try to analyze some situation which is not designed.
I have a question about definition of Nash equilibrium. Please show the slide where it is definition. Maybe we should put here start when S minus E and then with the inequality, because as it's written here, it looks like Nash equilibrium or strategies dominated, strictly dominated all other strategies, no matter what others play, other opponent plays. Maybe we should put star. No. No. Question is that in this inequality, all Nash equilibrium is strategy. Nash equilibrium is strictly dominated. All other strategies for every for no matter what other players play.
This would be a definition of undominated strategy, right? So if you try to do this, if you want a strategy which gives you as good payoff as any other strategy, it would be it would be not strictly dominated, weakly dominated. But so
Each strategy is strictly dominated all other strategies. Yes.
no. So in Nash equilibrium, we fix a strategy S minus I, and we only look at how your strategy plays against that particular strategy. I think that what you are proposing is that we don't fix this particular strategy, but we'll look at all possible strategies.
We fix strategies that are playing as a plays. Playing, there should be also Nash strategy, Nash equilibrium. So
Oh, yes. Okay, so surely it was a sloppy definition. As I should have said that this is true for every player. Yeah. So I think that what you are saying is that this definition is, no, actually, for each player, no, I think that it is actually not a sloppy one. Yeah, so I fixed a strategy as star.
Other players also expected to play Nash in Nash equilibrium, so we should put star from
Okay. Now I got the question, and it is absolutely right comment. So it was not a sloppy definition, but it was incorrect definition in a sense that S minus I should have been with a star. That's right, absolutely.
I have a question in general about the way we present these kind of games. And my feeling is, could you present the matrix again?
The one which is in the very
first one
beginning.
we just had on the screen. We just flew by that one. Yes. So my difficulty is often people think of this as payoffs. And if you think of that as payoff, it's very confusing because it's really utilities you're showing. But most often people think in terms of payoffs, which is very different. Because in a lot of these experimental games, we find that in people's utility, it's not only their own payoff, but also the payoff of the other. And the sharing of the payoffs. And that's this whole thing with ultimatum games, that if the sharing is too unequal, you rather have zero and punish the other one. Mm-hmm. And the problem with this presentation, I always find, is you cannot make a difference between the utility levels and the payoffs. So this presentation doesn't even allow reasoning about these things. So without, for example, you could make this game differently. Assume these would be payoffs, right? Assume these would be payoffs, not utilities. And the right side, I could rewrite it. And I could say, okay, instead of 0, 0, it's 10, 2. Instead of 3, 0, it's 13, 2. And instead of 12, 0, it's 12, 2. Then you would say, okay, right is the dominating strategy because it's always 2 instead of 0. That's more than 1. But we know from experiments that actually, in many cases, they will choose left anyhow. Because if it's 10, 2, we feel it's too unequal. And I'd rather have 1, and the other have only 3, than I have 2 and the other 10. But the way we present it, putting utility without allowing payoffs, does not allow us even to think about this. So my question is there a literature that tries to do that and tries to separate these things?
I think that I probably would only partially agree with you. So especially thinking about this particular matrix, it is no problem to put the right utilities in there. You have a particular choice, strategic choice, and a strategic choice, and then you know what utility each particular player has. So it is right that when we see those numbers, we think about, and especially we are connecting it to the experiments, then we are thinking about the experimental payoffs. But it is no problem at all to, especially in that sort of simpler games, to put the right utilities. So you don't know how exactly people feel. This is true. It is a difficult task. But this is probably a task for decision theorists or something like this rather than for game theorists. Thank you.